Hello everybody, my name is Andre Bauer, I'm from the University of Würzburg, and today I would like to present our work on an automated forecasting framework for seasonal time series. Before going into details, I would like to motivate our approach. Nowadays we are living in a fast-paced world. Due to the digitalization, new services and applications will arise. Existing applications will get more interest, less interest, or will even disappear. Moreover, the connected devices will increase. That means we have to handle a lot of complex workload in the future. One possibility to handle this is cloud computing, because it allows us a lot of flexibility. However, cloud computing or the resource allocation in cloud computing is quite complex, and therefore we need an intelligent mechanism to handle it. Indeed, one could say we could use a naive resource allocation, but all data centers together consumes 2% of the world's electricity demands and emits as much CO2 as the airline industry. For the sake of our planet, the naive resource allocation is not an option. Therefore, the resources in the cloud shall be supplied in an automatic manner and proactive. Current approaches observe the load, and based on the load, they either release or add resources. In order to be proactive, we have to know when we need resources and how much resources. To this end, we could perform different forecasts, each resulting in a different future, and therefore we need a reliable time series forecasting method. Indeed, there are different forecasting methods, each with its drawbacks and advantages. Here, for example, we have two different time series. On the left side, there are statistical forecasting methods, and on the right side, we have forecasting methods based on machine learning. As we can see, the forecasting methods behave differently on the two time series. In more general, there is the so-called no-free lunch theorem. It says that there is no globally best forecasting method on all time series. More precisely, it means if we tune or optimize one method on a given time series, it will get worse on other time series. To tackle the no-free lunch theorem, different hybrid approaches had been proposed during the years. We group these approaches into three groups, and the first one is ensemble forecasting. Here the idea is to use a set of forecasting methods and perform a weighted ensemble forecast. The second group is forecast recommendation. Here we learn on a training set which method performs best for a given time series. And if we have new time series, we calculate the characteristics and ask the recommendation system. The last group is forecasting decomposition. Here the idea is to decompose the time series and then forecast each component with its best forecasting method, and in the end the parts are assembled again. Our work focuses on forecaster recommendation and decomposition. We pose ourselves in our work three research questions. The first one is how to build a hybrid forecasting framework for seasonal time series. The second one is what are suitable time series characteristics for the recommendation. And the last one is what are suitable approaches for the recommendation system. To answer these questions, we have the following contributions. The first one is we create an automated framework for forecasting seasonal time series. We introduce a new set of characteristics and design three recommendation approaches. And we had a broad evaluation. In this presentation, we will have a short look at the forecasting framework, we will have a deeper look at the recommendation approaches, and we will talk about the evaluation. The high-level steps of our forecasting framework are as following. First, we simplify the time series with logarithm function. Then we extract features of the time series like Fourier terms, and we decompose the time series into its components trend, season, and remainder. Then we calculate characteristics like the mean of a time series and consult the recommendation system that gives us the best machine learning methods. When we forecast each feature with individual methods like the trend with ARIMA, and when we train the machine learning methods and predict the future forecast with the forecasted features. Before we could use our recommendation systems, we have to train it offline. Therefore, we have a time series storage, and for each time series and each machine learning method, we perform forecast and evaluate it. And when we save this forecast into a database, the methods are called base level methods, and for each time series we have a vector with the prediction accuracies. At the same time, we extract for each time series its characteristics and save it also in a database, and the characteristics are called meta-level attributes. When we join both datasets to a meta-level dataset, and this information can be then used for a recommendation. The first recommendation system is a classification task. Here it gets as input the accuracy of the machine learning methods in consideration and the time series characteristics. And when in a multi-class classification, it trains a random forest model that predicts for given time series characteristics the best methods. In the online phase, when new time series are given, characteristics are calculated, feed into the random forest model, and it returns for each time series the best method. The second approach is based on regression, and the idea is to model for each method its forecasting error. Therefore, we have the same input, that is the time series characteristics and the performance of each method. When we use regression to train n random forest models, one model for each forecasting method, and then if we get new time series, we use the time series characteristics to predict the estimated errors of the forecasting methods, and then we choose this method with the lowest estimated error. Our last approach is a hybrid approach that combines the regression and the classification task. It gets the same input, and with regression n random forest models are built. Each model represents a machine learning method and models the forecasting error. Here the clue is that we compare the forecasted error with the actual error, and then we use this difference to train another random forest model via classification. What method is the best after guessing its own error, and when we have new time series, we can calculate the estimated errors of each method, and then the classification choose the best method for each time series. As I mentioned before, we had a broad evaluation. We consider a lot of machine learning methods. We evaluate the rank and the accuracy degradation compared to the best method in the recommendation. We compare different recommendation approaches. S star has knowledge about the future. It's the best recommendation system and is a theoretical construct. SL choose the method that has the lowest average degradation in the training set. SB choose the method who was the most best method in the training. AC, AR and AH are our approaches, and we compare it with state-of-the-art forecasting methods. Our dataset contains 150 seasonal time series from various sources. We perform 100 splits with 100 train and 50 test time series, and from the trained datasets we create 10,000 new time series for each training session. This table shows the forecasting degradation based on recommendation. As I mentioned before, S star is a theoretical construct and acts therefore as a baseline. The best degradation regarding mean and standard deviation is achieved by the hybrid approach. We also compare our whole framework with different recommendation approaches with state-of-the-art methods, namely ETS, TBATS and SREMA, with forecasting error is called MAPE. And if we look at the mean, each approach has a lower forecasting error than the state-of-the-art methods. And if we look at the standard deviation, it also holds true, and the hybrid approach has the lowest standard deviation. That means our forecasting framework is able to reduce the forecasting error and also to deliver robust forecasts. Before I conclude my talk, I want to sum up. We talked about that forecasting is an important task for many decision-making fields, for instance in cloud computing. The problem of choosing the best method is the no free lunch theory, because there is no method that outperforms all methods on a given time series. Therefore, our idea was to propose an automated forecasting approach based on time series decomposition and method recommendation. And our experimental results show that our recommendation approaches perform almost equally, and the whole approach outperforms existing state-of-the-art forecasting methods. These are the references of my work. And finally, thank you for your attention.